In this chapter, we'll be talking about moment-generating functions. Now, a moment-generating function of a random variable is defined as the following. That's m, big M, sub x of t. Well, that's the moment-generating function, right, of a random variable x. That equals to the expectation of e to the power of t times x. Now, if we're dealing with discrete random variables, then the moment-generating function equals the expectation, as we said, of e to the power of tx, and that equals to the sum over all of k, right, where x equals k, of e to the power of tk times the probability of x equaling k. Now, if we're dealing with a continuous random variable, then the moment-generating function equals, again, the expectation of e to the power of t times x, and that equals to the integral over all of x, right, of e to the power of tx times the density function of x dx. Now, this may sound a bit confusing, but it'll all get cleared up once we go to an example. So let's just continue for now. The nth moment is defined as the expectation of x to the power of n. So the nth moment of a random variable x is obtained by taking the nth derivative, right, by t of the moment generating function, right, m sub x of t at the point t equals 0. That means that m, right, the nth derivative of m sub x at t, where t equals 0, well, that equals to the expectation of x to the power of n. For example, if we're taking the first derivative, then we'll get the expectation of x to the power of 1, or the expectation of x. Now, if we're taking the second derivative, right, then we'll get the expectation of x squared. Okay, that's all where t equals 0. Now, there's a theorem that says that there's a one-to-one correspondence between a random variable and its moment-generating function. Now, at the end of this chapter, there's a list of special distributions with their moment-generating functions.